All right, let's get right into it. We are on the trail of a cosmic cold case, and our journey is going to take us 1,600 light years from Earth out to the constellation Puppis, where a single dead star is waiting to tell us a story that could basically rewrite the book on how stars live and die. I mean, it's a huge question, right? How can one tiny little point of light, this stellar ghost, hold clues to the biggest questions in the cosmos? Well, as we're about to see, this one star is an absolute treasure trove of them. And here it is, our scene of the crime. This is Messier 47, this big, sprawling collection of stars where our whole mystery unfolds. Think of it like a cosmic neighborhood where generations of stars are born, live, and die together, leaving behind all the evidence we need to piece together their incredible stories. Okay, so before we zoom in on our main suspect, we've got to get the lay of the land. You can't solve the mystery without understanding the scene of the crime. So this is Messier 47. It's what we call an open cluster, which is really just a fancy way of saying it's a big, kind of loose family of stars that were all born together from the same cloud of gas. It gets compared to the Pleiades a lot, but some astronomers lovingly call it a more ratty collection. Now, the crucial clue here, the most important thing, is its age, about 150 million years. And that is the absolute sweet spot. It's the perfect age to find young, hot blue stars still shining bright and the dead remnants of the ones that already burned out. So, the first step in any good investigation, you gotta clean up the crime scene, isolate the evidence. On the left, that's the raw view of Messier 47. It's a total mess, right? It's swimming in a sea of background stars from our own galaxy that have nothing to do with our case. But then, astronomers do some incredible forensic work. They use data on how the stars are moving to filter out all that noise, and boom, on the right, you get a clean view of the actual cluster members. So, why Messier 47? Why go to all this trouble for this one cluster? Well, it turns out that special age we talked about makes it the absolute perfect spot to go hunting for a very particular kind of, well, a stellar corpse. We are hunting for white dwarfs. See, when a star up to about 8 times bigger than our sun runs out of fuel, its life comes to an end. It just puffs away its outer layers, and what's left behind is this unbelievably dense, scorching hot core. Seriously, try to wrap your head around this. The entire mass of our sun squished down into a ball the size of planet Earth. It's mind-boggling. That's a white dwarf. And that is exactly why Messier 47 is what astronomers call a happy hunting ground. At 150 million years old, it's been around long enough for its biggest, brightest stars to live fast, die young, and collapse into these white dwarfs. But, and this is key, it's still young enough that those white dwarfs haven't had billions of years to cool off and fade into blackness. They're like little cosmic embers, still glowing hot, just waiting for us to find them. So, a team of astronomers went on the hunt. And you gotta understand, they were sifting through mountains and mountains of data. And then, they found something. One single, faint little object that just stood out from the crowd. A peculiar suspect that needed a much closer look. So how'd they do it? They used data from the Gaia Space Telescope, this incredible mission that's building a 3D map of our galaxy. They were looking for an object that checked all the boxes. It had to be at the right distance, moving in the right direction, at the right speed. Basically, it had to be flying in formation with the rest of the Messier 47 cluster. And after all that painstaking work, they got a hit. Just one. A perfect match. They had their target. Okay, so now they've confirmed the suspect is a true member of the gang. It was time for the interrogation. And the way you interrogate a star is by breaking down its light. You can force it to spill all of its deepest secrets just by analyzing that faint little beam. And what they found, well, it was weird. Really weird. This was no run-of-the-mill white dwarf. The evidence started painting a picture of a star with a very strange and totally unexpected history. Okay, check this out. Clue number 1. Its light fingerprint, what we call a spectrum, showed it had an atmosphere of pure helium, which is pretty unusual for a white dwarf this big. Clue number 2, and this was the real bombshell. Every single line in that fingerprint was split perfectly into 3. And clue number 3, there was this faint hint of extra red light, which told them our suspect wasn't working alone. It had a partner, a small, cool companion star orbiting it. Okay, let's focus on that split light, because that is everything. It's a classic forensics clue in astronomy called the Zeeman effect, and it only happens one way, when you have an absolutely monstrous magnetic field. The field is so strong it literally rips the energy levels inside atoms apart, which makes the light they give off split into these triplets. This was it, the smoking gun. So just by measuring how far apart those lines were, the team could calculate the magnetic field's strength. And the number they got was just staggering. 250 Tesla. Now, to put that in perspective, a powerful MRI machine in a hospital, the kind that can pull a metal wrench out of your hand from across the room, that's about 10 Tesla. This star's magnetic field is 25 times more powerful. It is without a doubt one of the most magnetic white dwarfs ever found, period. But here's where the detective work gets really, really brilliant. They wanted to figure out what this star was like before it died. So they worked backwards. They know the cluster is 150 million years old. From the white dwarf's temperature, they figured out it's been cooling for about 76 million years. So you do the simple math, subtract the cooling time from the cluster's age, and you get the original star's lifetime, just 74 million years. And in the stellar world, a shorter life means a bigger star. A star that only lives that long had to have been a beast, about 6 times the mass of our own sun. So let's just recap what we've got. An extremely magnetic, massive white dwarf with a rare helium atmosphere and a tiny companion that was all born from a star 6 times heavier than our sun. You've got to be asking, so what? Why does this one stellar corpse matter so much? Well, it's a huge deal for a few massive reasons. First, it throws a giant wrench in our best theory for how these monster magnetic fields are made. The idea was you had to violently smash 2 white dwarfs together. This star says, maybe not. Second, this little 2-star system is a potential ticking time bomb for a Type Ia supernova. Those are the special explosions we use as standard candles to measure the expansion of the entire universe. And third, some of our best models of how stars work, they basically said a massive helium atmosphere white dwarf like this just shouldn't be possible. And yet, here it is. It exists. In fact, the research team that found it called it a potential Rosetta Stone, and that is the perfect name for it. Just like the original Rosetta Stone unlocked the secrets of Egyptian hieroglyphs, this one star could be the key that helps us decipher the mysterious link between massive stars, their powerful magnetic fields, and the exotic things they become after they die. It's really an amazing reminder that some of the biggest cosmic clues aren't hiding in some exotic, faraway corner of the universe. They're tucked away in plain sight, inside star clusters we've known about for centuries. It just makes you wonder, how many other Rosetta Stones are out there, just waiting in the star fields for us to finally find the right way to read their stories?